virtual environment, around COVID. But just putting this out here that, feel free to just raise your hand and ask any question. So let's move on. Okay, so the objectives for our hour and a half today. I know this was shared in the agenda, but I also sort of mentioned a little bit early on, we had a few more people join in, but really we want to provide the theoretical background for both machine learning and deep learning. And this first day is going to be on machine learning, second day is going to be on deep learning. And it's really to start getting everyone's gears turning on different workflows, how you're currently doing some methodologies and how maybe machine learning or deep learning could complement that. We also want to grow West Africa's interest and skill and ability to participate in the TensorFlow working group, because the initial idea back in 2019 of the working group was to have a space that is open for dialogue, for people to ask questions, to develop, to really sort of come up with ideas. So, we want everyone there to be feeling as though they can participate. And I think this 3-hour session could be a great stepping stone in that direction. And also we wanted to have some time for folks who are attending the Geo for Good event to also have some hands-on knowledge and experience as well. So there's those elements here. So as I mentioned before, expected outcomes, some knowledge and expertise in machine learning, deep learning, and the ability and interest to participate in the TensorFlow working group. So as I mentioned before, day one, day two. Day one is all machine learning. Day two is all deep learning. We're going to do theory. So what is actually happening in a random forest? We're not going to talk about all types of classical machine learning because it's a really, really broad field, but we'll go into one example. We're going to have a test. So that's the first warning here. Put on your listening, your thinking caps and your listening ears. I don't know what the term would be, but there will be a test. It'll be really hard. So you have to pay attention, take notes. And we'll also have a winner of that test. So we're setting the bar pretty high. And hopefully I'm scaring everyone just a little bit in a fun way, right? And then we have a hands-on lab and then discussion space. So within an hour and a half, we're going to try and do a lot for 2 days. Okay, so this is a great time to check if you have access to some of the resources. Let me just share this repo really quick. It is publicly available, so everyone should have access to it. It should be listed in your, let me open up the pointer here. Turn on laser pointer. It should be listed under your reader. So when you click on that link, since it's open to everyone, it'll pull up as an available repo that's got my name and this West Africa machine learning training. And there should be 3 scripts in there, not actually 2, but this is an older screenshot. So if you don't have that, when you click on it and let it refresh a few times, if you don't have it, just raise your hand and we can workshop it while we're rolling through the theoretical. Okay. So as Glory has kindly been sharing the pre-training survey, definitely fill that out. We want to hear, we want to collect the information on demographics, interest, background. That's really helpful for us, not only just for folks we know really well in the hub, but also just really broadly. How does this type of machine learning training help? As it also goes into our sort of global thinking on the usefulness of the TensorFlow working group. And at the very end, I know we'll have a summary report that will help to underscore, how useful this type of training was. So please fill that out, and I'll just keep turning along. So at the very beginning, when a couple people, while we were waiting for a couple more people to join, I shared this Jamboard. It's here again. Feel free to fill that out. It's just a couple of blurbs about who you are. For the sake of time, I'm just going to zoom forward. And if we get time at the very end, we'll come back to this introduction so we can meet people a little bit more. I know you guys all know each other, but I don't know everybody. So we'll save some time because I know there's like 42 people on the call and we would basically eat the whole hour. But we want to have that. So, oops, let me go back to that. Okay, so now we're going to switch over to Menti. Very quickly, if you go to join at menti.com and then use this code. So just in another tab, you can put in that 64978281 and put in what you initially think. So this is an interactive portion. What do you think of when you hear machine learning? And this should update live as people are putting the responses in, hopefully. Fingers crossed to the demo gods are working well with me today. So image classification, data science, what else? We'll give it like 4 or 5 minutes as people sort of get their gears turning. It's really helpful to understand what people are coming in with, what knowledge they have, maybe what their use is. Data science, deep learning, artificial intelligence. Image processing. Random forest, regression, classification. Yeah. What else was added there? Automation. Trying to read these ones horizontally. Instance segmentation. Yeah. So like as people are still adding these, I mean, my takeaway here from this list right off the bat is there's a lot of different uses, right? There's a ton of different uses. Some of them are very specific. Some of them are relatively broad, like a whole field, like data science. But then there's some that are hyper specific on, instance segmentation. So I think, keep adding, your thoughts in here. I see that automation is popping up as a touchstone. The larger the text, the more the higher frequency of submissions here. So yeah, I mean, magic. Oh, I love that one. Is that a meal? It's great.
It was not, but
that's hilarious. Yeah, there is a bit of a magic feel to it. I'm surprised no one has put in black box either. So that's the double-edged sword, right? There's some really fantastic things you can do with machine learning and deep learning. And then there's some caveats, and I'll be frank about those, and Biplav as well, about good applications and elements in which you should be cautious, right? This isn't a panacea that won't fix every problem, but it's another tool in your toolbox. So great, we've got a lot of responses here. Let's zoom to the second question. Okay, rank your skills and knowledge using machine learning from 1 to 10. So from I don't know to you're a wizard. How skilled are you? Ooh, we've got an 8. This is fun. I love these mentees because it's like, it's live. You can really see people interacting. It's fun. We'll give it a couple more responses. I know you guys are already inundated with surveys, but this is just one more temperature check on where everyone's at. But it's cool to see that, we've got not so much a normal distribution. We've got this kind of, I don't know what waveform this would be, but we've got quite a few folks at 4. Ooh, we've got a couple more experts. That's great to see. So it'll be interesting where we're sort of tailoring this training. Right now, we're going to start relatively basic, right? And then we'll progress through this day 1, and day 2, we're going right into deep learning. So this is really focused towards that machine learning, but it's great to see where everyone's kind of coming in and self-classifying too, which is, always fun. So let me switch back to this tab and we can get rolling. Okay, so I got to make sure that I'm asking the specific questions for the test and don't leave you all hanging when it's test time. So this is a relatively useful diagram, I think, for understanding the history of artificial intelligence, machine learning, and deep learning. And you can see here that artificial intelligence, the way it has been until recent memory, has been really talking about a broad field, right? And now with like Chat GPT and generative AI, folks are sort of using that terminology to talk about a very specific type of application. But if you were to take a couple steps back, AI is really sort of like a whole field, with machine learning being a smaller field inside of that, which is very well mirrored to statistics. So this is like a computer science, applied science mirror to some statistical approaches. And then within that, a smaller field, and you can see here the timeline around the 2010s timeframe, deep learning started to come into vogue as well. And we'll talk about why that is. But you can see here, really think about it as these subsets. So we're starting a little bit more broad with a lot of the advancements, even though machine learning had sort of existed before the 1980s, that's when more and more algorithms were coming out, and it was more and more user friendly. With like now you can just pull up SciPy and use machine learning. Before it was very, very complicated. So that's the rough history. So this day one is just on machine learning. Okay, so as we're talking about the breakdown of different fields, there is two camps I would mention. One is unsupervised and one is supervised learning. And really what we mean by supervised learning is you're given the data with labels. So if you're trying to identify rice, you have existing rice labeled points or annotated points that have that information. And then when the model runs and creates that relationship and you introduce new data, it's able to leverage that past prediction, past knowledge to predict on new instances. So that is all supervised. It has the information to begin with. Versus unsupervised, it doesn't have the information. You're not providing that label to begin with. So think of like clustering when you've got data on an X and Y and you've got points within that scatter plot. You're using like a nearest neighbor clustering algorithm to identify the actual distance between those points and the clusters of those points. So you don't necessarily need a label to tell you what's rice and what's not rice, or what's galamsey versus not galamsey. So those are just different approaches within a data space that you can use to segment your data. And we've highlighted this top section here on machine learning. Many folks are probably familiar with regression. It's probably the most common sort of approach, in modeling. And we'll talk more about random forest today. But there's SVM as well. And I'm sure folks are very familiar with that as well. So we're really only going to be talking about supervised learning because that tends to be the area, especially in the EO world, that we interact with in the most. So I know this was shared with the prereqs as well, but for everyone who's really interested in this as well, and you haven't had this opportunity, this is a 10-hour training from Google on machine learning and deep learning. I would highly recommend it. There's still time to listen to what you can between now and this time and until tomorrow. It's just a really great resource, and I actually come back to it every year or so because I find it really relevant. As I'm reading more papers, I come back to it and I have a lot of aha moments. So check it out. It's a free resource, and put that as something you can leverage in the future if you haven't done it already. Okay, so as I mentioned before, there's a broad field of machine learning. Zooming back to this slide, you can see the different algorithms here. But this is I kind of like this as a sort of a network diagram. And most folks are probably interested in, when we looked at that Menti, like image classification, right? It makes sense with the Earth observation field. We're looking at trying to identify features within an image. So having something like an image classifying algorithm could really be really powerful. And that falls way up in this top corner where we've got classification, which is a type of supervised learning, which is within the field of machine learning. But you can see these different, essentially, camps where algorithms are performing differently. And really, we can think of machine learning as it's building a model off of that sample data. So that's known as our training data, right? And that's in order to make these predictions. So the beauty of this is when you give it enough data and you allow the model to build this relationship, you're not having to explicitly go and label every single pixel as Galamsey or not Galamsey. You're allowing the model to make that prediction. So on a scale sense, this is really, really powerful because if you're dealing with millions of pixels, it's okay if you have a little bit of error because you just saved yourself an insane amount of time not labeling every single pixel, right? So there's a lot of upsides to it. So think of sample data or training data with those labels and the ability to make predictions. So let's walk through a thought example here. I had a really useful time when I worked at Colorado State, and I had a postdoc who was a great teacher, and he explained, like, think of everything as tables, Tim. And that really had kind of an aha for me because when you're doing all this geospatial processing, you're dealing with rasters. Oftentimes the operations are kind of like tables already, right? It's an array. And then when you get into the data space, what you have to give the model is a table, essentially, right? You've got your points or your pixels or what have you with your labeled instances. So that's your rice or non-rice, or your Galamsey or non-Galamsey for these binary classifications. And then you've got all these features. So you've got like NDVI and Savvy and occurrence of water or distance to roads. So each one of those columns, each one of those features is going to be a column with an ID next to it. So when you give this to an algorithm, it's actually just synthesizing that table. It's taking that information in, it's assimilating it, and it's allowing it to draw conclusions based off the information. So on the data science side, take the time to sort of know and think about the qualities of your data going into the model. So we've got this example here with this tabular data where we've got cats and dogs. So the things we know about cats and dogs is maybe in this hypothetical table, we've got for entry number 1, we may know if it's a cat or a dog. We may not know that information, but we know its size, its weight, its color, its ear length, its nose length, all these attributes about that individual entry. So it may or may not be a cat or a dog. We don't know, but we know all these other attributes about it, right? So how can we, given that information, this huge table with all these different fields, how can we predict to make a binary classification if the next entry that we get is going to be a cat or a dog? So let's just, I'm a very visual learner, so let's walk through this example here. So we've got 2 entries. Entry number 1 is this bottom one. Entry number 2 is the top one up here. And we can see here for nose length, we might actually have a relatively small nose length versus this nose length. And the size is also vastly different. So with this feature here in this first model, if we only had 2 entries, it would try and, with a machine learning algorithm, essentially it would try and draw a line. This would be a hyperplane or a decision boundary. It's just really just a fold in the data. It's trying to say within this data space, I want to draw a line where these 2 groups are different. And that, in a very straightforward way, is a classification, right? That is, we've made this decision between these 2 populations, and then now anytime I get a new population, I'm going to make that prediction, right? But we want to really look at our whole table. So let's add some more information. So we've got an instance here. We've got a much smaller nose, but a much larger size. You can see here how that hyperplane has changed a little bit with new data, right? And if we do that again, you can see here we added even couple smaller animals. We can see a different hyperplane. And finally here we've got a location where this might be really confusing, where a dog is about the same size as a cat, maybe the same nose length, but the ears might be the distinguishing feature. But it's not listed here, right? So this hyperplane, this approach that divides these two entries that you're interested in, your focal entries, this is a really key factor about, understanding the quality of your data and what algorithm you're going to use to find the solution. So in a very short, very concise way, this is the majority of how most machine learning algorithms are making decisions based off of the input data. So it's looking at those features and it's developing a relationship based off of that data. So in that blue box, the key takeaways here are training data. So you've got your Galamsey points with a labeled Galamsey as this location as being a Galamsey point. We've got prediction, or AKA inference. That's where say you've got a point at location A and at location B, you don't have a point. So how do you know if that is a Galamsey location or not? That's where you'd rely on the model to predict to that new pixel. And when I say inference here, that's a statistical term that for folks in the machine learning world, they tend to use the word prediction, but inference often means relatively the same thing. Slight nuances there we can talk about probably on day 2 if anyone's interested. And then for the next bullet there on input features, or AKA model covariates, that's what I mentioned before with like nose length, ear length, size, weight, things like that, those attributes about the individual species. You can think about it the same way as like Galamsey. We've got a location where there's a point where we know there's Galamsey happening, and then we've got all these other attributes about it, the change in NDVI, the forest cover type, the distance to roads, the distances from waterways, all these other attributes. And they don't necessarily have to be just EO derived. They could be, really whatever. But that's the input features. And then classification, you can think of it as like a binary classification. All my examples thus far have been like rice, non-rice, or forest canopy versus non-forest canopy. But you can also have multi-class. You've got many different types of entries, and you're using that to predict 10 classes, and the model can do that as well. There's abilities to do regression as well. So in the canopy cover example, if you had 10% canopy as an entry and 40% canopy as an entry, you could use a machine learning algorithm to identify at what point you could start to identify canopy at a certain percentage of that canopy as well. So you can use not only categorical information, but continuous data as well. So we've got this example here. Again, we think of it as table data. We have this database of Galamsey and non-Galamsey GPS points. So that is this instance right here, with blue being non-Galamsey, blue being Galamsey and red being non-Galamsey. And you can see my cursor is also red, so that might be a little confusing. And we've got this set of Landsat images. So how can we use this information to really start answering the questions of where Galamsey might be? So we're going to walk through another example here. So let's leverage some of the information from EO that we can derive. And this is just these might not be the best features, right? That's where you can start to blend your knowledge, your environmental management or environmental knowledge, ecosystem management knowledge with what are the right variables to understand this phenomenon, because that's really key, understanding the geophysical properties and coming up with proxies for those or direct measurements of them with Earth observations. that are relevant to that feature is so critical in creating a valuable model. But we've selected in this example here, SAVI and NDVI. And these are just median composites between 2019 from May to October. So it's just an arbitrary time with an arbitrary index that's a median. And we can see here in this example, we've got a pretty stark two classes, non-Galamsey versus Galamsey at the top. And obviously when you're running in this graphic here, we've got the number of trees that are running through this calculation to identify this hyperplane. And essentially all we're doing is that line ends up being the model, as I had mentioned before. So how do we then take in new information, right? So imagine there's only 100 points here within this data space, and that's all the points for for your field campaign, right? This doesn't have any geographic information. It just has only information plotted by NDVI and SAVI. So if we were to add in a new point or a new location that has SAVI information and has NDVI, where does that point fall? So let's walk through this example. So we've got this brand new location. It ends up having a -0.3 and a 0 for SAVI. And we can see that it's most likely going to be not Galamsey because it falls within this space, right? And that's really sort of how you should start thinking about the data space and machine learning algorithms, because they're taking the relevant geographic information, but then when they're stepping into the data space, they're shedding that geographic proximity. There are ways to include that in the modeling space, but for this random forest example, it's not being included, right? It's only looking at these and comparing these features, which are SAVI and NDVI. So that's essentially what's happening here. So as I mentioned before, hyperplane and decision boundary are really key factors in identifying these two different classes in this binary classification example. So how will we actually leverage machine learning to answer these questions? So there should be you should be asking yourself going into using this tool set, what's your input data? So like for instance, Galamsey, we had those known locations of non-Galamsey and Galamsey points. But oftentimes as like technical implementers, all of us in the room here, you might just be handed a data set. You're probably not the person going out collecting the information and running with it all the way to the final product. You might just be right in the middle, right? So someone's handing you the data and then you're charged with sort of producing something, which is great. Like I love being in that sort of middle space, but I always like to take a full stop there and understand the input data. So what is the data type? What's the quality? What's the quantity? What's the evenness between the classes? So do I have 10 million Galamsey points and only 4 non-Galamsey points? And if I'm trying to build a model off of that, I'll probably have some biases or imbalances to begin with, which is really going to influence my model. So I'm trying to develop a relatively even distribution between those classes, because that's really going to be really important. Also, another factor to think about is spatial distribution. If you're going to be collecting all of your points down by, say the ocean in Ghana, and you have like a high concentration of points in one location, but then you're trying to model that same phenomenon, but thousands of miles away, that's going to be really challenging, right? So having a really widely distributed and evenly distributed point collection for the phenomenon that you're trying to identify is going to be really critical. And you want to take advantage of that variability, both geographic, environmental, because if you think about it, say you're trying to identify salt, right? You've got a dried up lake and you've got a salt bed. And from an Earth observation, salt is bright white, maybe surrounded by desert. So it's pretty easy to identify. But then, you might have some salt distributions that are in other environmental cases. Might be some mine tailings or things like that. And if you're not capturing that spatial variability, or even like the human intervention variability when you're collecting those points, your model won't know how to handle those new inputs. So really think about the quality of the data that's handed to you, and that also will change your approach when you go to actually do the implementation, right? You may have to scale way far down, like your geographic prediction, if all of your points are concentrated in one location. So those are some of the caveats that you should be thinking about, and as sort of rules in your toolbox when you're thinking about applying this. Okay, I see a couple questions here. Yeah, go ahead, Emil.
Yeah, thank you, Tim. Maybe also just something to consider too. For there that you have on the slide talking about key factors with input data. I guess we often think about the input data in terms of like the field points or what have you that we're collecting. Something else obviously to consider is the appropriateness of the imagery that we're using, right? Like, so let's say we're doing classical type classification as you pointed out, of you're doing a supervised classification, maybe using Sentinel-2 imagery, maybe using LATSAT-9 imagery, what have you. Also considering the intricacies of that data itself, right? Folks in West Africa, like folks in other parts of the world, now also exposed to data from Planet, data from other sources. I think you brought up hyperspectral imagery perhaps a little earlier, Tim, and so like how the number of bands that are available come into play. Whether the data, for instance, have shortwave infrared, they have additional additional spectral information that some types of imagery might not have. And also, of course, the reason I brought up the idea of the imagery as well is how we're processing that imagery. Are we collecting the imagery from, say, an appropriate time of year? Are we doing additional types of processing on that imagery to essentially kind of match it up to what we're looking at? And so just to throw out that there are additional kind of things that go into it, because as Tim kind of highlighted earlier, I guess you didn't put it into those specific words, but I remember like when I was in grad school being exposed to some of this stuff, the traditional term that they'd say is garbage in, garbage out. And so lots of times we think that, oh, this model didn't work properly, or I'm not getting the outputs that I want because the input data I have isn't correct. But I guess there's the intricacies of not just your field data, your satellite data, the algorithm that you're using, how you tune it, et cetera. And obviously with Tim and Biplav, we're going to get into some of the intricacies of that as well. And I guess I know that there are other people have other questions in there as well.
Yeah, Emil, fantastic point. Yeah, the other element, being really mindful of the variable space, those covariates that you're adding. And you said the key word there, garbage in, garbage out, key words, I should say. That is so critical to even produce anything of value, right? And I think most everyone knows that already in this call, but it's so critical because the model will only it'll only produce what you give it, right? So it's going to be making decisions off of potentially poor data. So that's where being really restrictive and thinking very deeply before just applying these methods. It's really important. Okay, I had one question in here. How do you evaluate the evenly and widely distributed suitability of training points? Great question. I would say it starts with expert knowledge, right? We're going to have an example here of Galamsey. I'm not an expert on Galamsey, right? So I should be probably invalidated to begin with. But if there's people who have that knowledge to begin with, they're capturing, unique instances of Galamsey mining. There's maybe high impact instances, low impact, large scale, small scale. Elements like that type of variability be really critical for the model to see. And then spatial distribution, if it's happening, if it's widespread, you want to try and capture that in a field campaign in the same way. And to Emil's point, you want Earth observation that also captures that same type of phenomenon, right? So you want to look at variables and include variables that capture that type of phenomenon, either for that time period or for that sort of optics or physics in the atmosphere. So definitely be thinking along those lines. And I would say just apply more scrutiny than you would actually ever, more scrutiny than you ever think you need. Just keep coming back to that question, because ultimately when you run these algorithms, you're just going to come back to then evaluating the quality of the model. So you just do this iterative process where you bring in data, you bring in your products, you run the algorithm, it runs like super fast. And then you have to understand the quality of it. Is this even useful or not? And then you just go back to the drawing board over and again. So it's very, very iterative, and taking that time to think about, elements about like how widely distributed the points are, how apt the points are for understanding the phenomenon, how useful the input data is. Those are all going to really improve your model, in addition to like the tuning of the model itself. So the different parameters that are happening within the random forest algorithm. So yeah, there's a lot to talk here, and we'll save that a little bit more for the discussion as well. Okay, and then the qualities and quantities of input data. Does it comprehensively identify a geophysical attribute, right? If you're trying to identify a specific thing, the indices that you're giving it or the proxy data, is that even really telling the tale? And you need to be thinking about it that way. And how much data do you really need, right? And what kind of data gaps do you already have? Those are just taking that time in advance of that. And we can talk about that in a little bit more. And then one more thing is getting kind of familiar with different algorithms, especially in the machine learning camp. There's a lot of different types of algorithms. They all do sort of similar things, especially in this image classification bubble. And the data that you might have might be more suited for a particular algorithm. And for instance, like random forests can run with relatively a small sample size, a small population, versus maybe Maxent, which might need a lot of points, or SVM might need something else. So when you're making your decision, understand your data first, and then you'll probably come to a conclusion about the best algorithm. And of course, that's where you could be coming to the TensorFlow working group and asking those questions when we get into a little bit more detail, because everyone's sort of going down the same sort of checklist when they're doing their applied science. So when I say thinking about your input data, this is a good way to sort of visualize it, because again, I'm a visual person, but is your data, does it have this linear quality, right? So if you think about Galamsey versus non-Galamsey, we don't know what these variables might be, but we can see here that it's relatively easy to draw a hyperplane, right? So like a regression algorithm or SVM or a random forest could easily pull this data apart. Like that's what they're designed to do. But then we might have something like this, where within this data space, there is this tight cluster that doesn't really interact with any of these other locations, any of this other space. So it might be like median house prices in a particular census or something like that is already geographically tied to, but then when you look at it in a data space uncoupled from the geography, we see this tight cluster. And that's where a clustering algorithm like a K nearest neighbor would be probably really successful, because it's not going to draw this really awkward hyperplane. It can just cluster those together as their own instance. And then we've got this location here where we've got really inseparable data. So we've got highly mixed data or tangled data, and we can't really use these two approaches. So on day 2, we're going to talk more about deep learning, which helps to draw really unique, potentially overfit types of hyperplanes, decision boundaries. And this is really relevant because it allows you to also apply more knowledge about your training data, like looking at a patch of information as opposed to a single point. So that's really exciting in the deep learning. Yeah, Emil, go ahead. Oh, did we lose you, Emil? Oh, mic not working. Okay. I'll just keep going.
Can you hear me?
Yes, go ahead. Go ahead.
I have no idea what happened just now, but just to say quickly, I really like the example that you brought out there, with the graphic on the bottom center, because I think it illustrates, just two things to quickly mention about this. I think a lot of people have seen this type of graphic or some version of this in different remote sensing books, and it kind of provides I'd say an idealized, what spectral signatures look like. And at least in the classical part of machine learning, they usually point to, ideally, you're going to see these big differences in spectral signatures between different types of things you're looking at. And so, again, just imagining, we have folks from different parts of West Africa. A problem set could also be, you want to differentiate two types of crops. You want to differentiate, millet from sorghum or maize from millet or what have you, right? And so ideally, in the ideal case, you have that there'd be spectral differences there. But of course, it's not until we actually do the testing that we realize that in many cases, it's not so idealized. That's one. And then the second part that you have there highlighted, Tim, regarding the visible bands, is kind of showing how, like for instance, let's say we're only using, data from Planet or one of these other ones like QuickBird, Iconos, et cetera, that only have visible and near infrared data. If the different features that we're trying to differentiate between are all like really close in the parts of the spectrum that we have data for, and we don't have the shortwave infrared where you have the big differentiation between the classes, then that creates a challenge for us to make those, to essentially tease things apart. But again, as we're going to see in the second part tomorrow with Tim and Biplav, I guess that's where these newer techniques like deep learning have come in to come up with different ways of separating these things. So I really like the example. Thank you.
Yeah, and this, as Milo mentioned, like this is such a staple. We've kind of like an ongoing joke in our office because we see this figure all the time because it's so especially this one up here. It's so telling of sort of what you're sort of driving towards when you're trying to identify that key physical property or optical property that really helps to distinguish the classes in your mind, right? You're sort of applying this data science lens and then this geophysical lens or applied science lens, and you're trying to merge them together. And another good example could be like elevation, right? You think of something so simple as we were doing this project in Bhutan, and we're looking at low-lying rice fields versus high elevation terrace rice. And it doesn't matter how effective, you can identify, the greenness of the rice or the wetness of the fields. The biggest telling factor was the elevation. Like that was one of the best features to begin with, just because of the way in which the rice is already cultivated. So knowing that kind of knowledge and taking advantage of it can be really, really useful in an informative input variable. Okay, so then we've talked a little bit about the different algorithms, and one of the questions or the elements I had here is get familiar with the different algorithms. And in the classical machine learning, this is not by any means all of them. This is just a few that you probably interact with, like a CART or BRTs or GBRTs or random forest. And I like this figure a lot because within that, like the past example you had right here, it's going to give you 3 or 4 decision trees, SVM, Bayes, and nearest neighbor. It gives you 4 different types of algorithms and how they're performing on this data, theoretically, right? And you can see here, they're all basically doing the same thing, right? And they might do it slightly different, but they're still segmenting that data. So, you can take advantage of any of these algorithms. Some might have pros and some might have cons, but they basically do pretty similar things. So I would say just be open to learning new algorithms, but also learn the caveats associated with them. And this is a good example of random forest, what's actually happening here. When we're developing these hyperplanes, it's segmenting this data space to say, I'm going to make a split here to segment this data here and then here. And you can see here with 3 lines that it draws, when it's segmenting this data, we end up with a pretty good classification with only 1 misclassified location. But then if you wanted to capture this and really push the algorithm, we'd end up having to create 6 total splits. And that's 3 times the amount of partitioning, right? Just to capture this one location. And this is a good demonstration of an overfit algorithm, because what happens when you get introduced with another red point that's right here? It's going to be misclassifying that. So you want to balance your specificity of the model with the flexibility of the model to interact with new data points. And this is really more about just, good modeling practices, but I love this representation of this is really what you're sort of interacting with when you're doing that iterative modeling stage. Okay. And then let's go hyper basic, like very, very basic. I gave this training to folks in Bhutan in May, and a lot of people were like, oh, that makes perfect sense. So I wanted to include it. It might be too basic, but I thought, let's just keep it anyways. So we've got this input of data, right? We've got 2 classes, ones and zeros. And within these classes, we can see here that there's some features. Some are colors. So we've got some red, we've got some blue, and we've got another feature which is underlined. Some are yes or no. So these 2 we can see are underlined and these are not. So looking at that top line, we want to identify a new location. So like we've got something that just popped in, and it's another 0 and happens to be a red 0. So how do we separate this, right? We can see it's kind of complicated. We've got 2 classes, a couple of features, we've got a new input. What do we do? So we can leverage a decision tree. So the first question you might ask is this new entry red, yes or no? The second step would be, is this underlined? So you can see here we've got an immediate segmentation right off the bat. We've got splitting this data yes and no, right? But we haven't been able to identify this. So we want to see if it's underlined, and we can split it again. So within these 2 rules, we can identify a location where this is not underlined, but it is red. So with a very simple decision tree, you can find out something that is relatively nuanced within your data. So we're just going to scale that way up with way more features, with way more complexity. But in a sense, that's what we're sort of driving at, right? So this is a great representation of something relatively straightforward, but we're going to apply that from one tree to many trees. So this is where we get into the world of random forest. And I always like to talk about random forest because it's probably the most applied version of machine learning. It's relatively straightforward to leverage. It's available in Google Earth Engine, and it really lends itself to a lot of the EO classifications that we already do. And the power of random forests is the ability to ensemble. So in this other example here, we had a single tree that came to a conclusion, right? But that's just a single decision tree. But where we make a forest is where we have multiple trees. So that's the beauty of random forest, is we have a single tree. Tree number 1 is coming to a conclusion. Tree number 2 is coming to a conclusion, and n number of trees. So you could specify, do this 100 times over, and then it's going to take a majority vote across all of these to identify the best class. So it's taking advantage of a large set of computations to come up with a final solution. So that's really powerful. That single tree has now become an entire forest. And then that random factor is on this next slide here. So the beauty of the random forest is if we stay up here at this very top in population P, we've got, say, 3 classes, a blue class, an orange class, and a red class. We're going to take a random subsample of this data to create our first random forest. So we're just grabbing these 4 points, for instance. Then we're going to replace that data and sample again. So that's random sampling with replacement. So we may get that same point, we may not. And you can see here, we're subsampling that population to create this randomness to begin with. So each of these trees has a different set of populations to build its relationship with. Additionally to that randomness, we also randomize the features. So for instance here, this single decision tree that we had in this last example that had, underlined 1s and blue 0s, that example, it looks at all these features simultaneously and it makes its final decision. But in this random forest example here, it's maybe only making a decision off of 2 features, right? So if we zoom right over here, feature number 1, feature number 4 are only used in this very short, this not very deep forest, this very short tree, I should say. So the beauty of this also is it randomizes the features that it looks at. So within each of these trees, not only is it getting a random set of entries for its population, a subpopulation, but also randomizes the features to make its conclusions. And it still then uses the majority rule across all of them. So you're getting a lot of variability mixed into the model across all these different trees. And that's super advantageous for understanding, really biased data, nuances of data, and also drawing relationships that you couldn't have thought of to begin with. You're allowing this algorithm to draw those connections. So the randomness is really, really powerful here. And something else that I really mentioned here is bagging. So that's when I talk about this random sampling with replacement, we're actually doing this bootstrap aggregating, and that's what's is bagging. And it randomly selects features in order to construct a collection of decision trees with controlled variance. So that controlled variance is really important because, again, it's going to look at all of your features, but it's doing them in these random subsets, right? So that's really powerful. And another factor here is when you look at, say, this population P, and you're pulling down this subpopulation, you can measure the out-of-bag error. How wrong essentially is this population for each of these trees? So there's different metrics that you can pull out of the valuableness of this modeling framework. So a couple other key factors that are in gray here, or this tannish color: number of trees going this direction. So you can do 100 trees, 1,000 trees, whatever. It allows you to add more and more and more variability, essentially controlling that variability, and the depth of these trees. So you can say, I want to use every feature. Essentially, if you give it 1 million features, it could be 1 million tree spaces long. But you don't necessarily want to do that. It'd be really computationally challenging. So these are some basically parameters that you can give to the model. And then it does this final ensemble. So this is a lot to consume, but this is sort of what's happening in the value from a random forest perspective. And we'll get into that with the remaining 30 minutes of this. So the pros and cons just for random forest, it improves upon the decision tree, that first example, because it allows basically a large committee. We have a huge set of trees. It's going to ensemble across all of them, many trees, and come up with a majority solution. So that's really valuable, right? It looks to reduce that overfitting by allowing bagging and also a metric for the out-of-bag error. So you can then deal with overfitting with this metric. You just have to be aware of it. It's easy to implement. It performs well with a low number of points. It's computationally inexpensive because all it's doing is basically drawing a statistical tree, and it's low effort. And then the cons is it can't handle tangled data. Like back a couple slides, we had that really tangled data. It's going to make a really overfit mess. One key bullet here I'll highlight is, if the problem is super simple, you may not need random forest, right? You may not need all of this magic, right? You might just need a simple linear regression, or maybe you're just looking at a spectral peak or something like that. So just because I'll get on my soapbox for just a second, just because you learn these skills and you have them becomes a hammer, and then everything becomes a nail. And I'm guilty of this. I'll use machine learning for things I don't necessarily need to. So just be aware of that. Don't overcomplicate it. And this algorithm is still very overprone to overfitting. You can take care of that with monitoring your out-of-bag error, but it's all about the application. Okay, and then Emil said it already, but this is really key. 2 major takeaways: the so what's, garbage in, garbage out. You're going to get a bad model if you don't spend the time understanding the qualities of your input data, your input features to begin with. It's going to be bad, and it's going to be within your side, your camp, to really understand why this is. So think about garbage in, garbage out. And then this last quote is from George E.P. Box, and this used to be when I worked at the USGS. This was in the modeling room above the computer. it said, all models are wrong and some are useful. So I love this quote because, this famous statistician is straight up saying that, we have all these tools at our disposal, but they're all going to be wrong, right? They're going to get pixels that are incorrect. It's going to misclassify things. Every model is going to be wrong, but it's up to you and stakeholders and the technical teams to understand the value of what's been created. So always keep that in the back of your mind that all models are wrong, but some are useful. So that's a great takeaway. So now we've got our hands-on lab. We've got about 25 minutes left. We might be able to squeeze a little bit of discussion in as well. So we're going to talk a little bit about Galamsey. And this is where I'll switch over to the Google Earth Engine. And just raise your hand if you can't get access to it. I shared it before that it should be in your reader. So let me switch that tab. Okay. And go right ahead. I think it's Frederick. Frederick?
From what you just explained on random forest, it gives me the idea that, for example, if 10 different individuals with same input parameters should run that model, they're likely going to have different results. Is that correct?
That's actually not correct, but there's something we'll talk about called the setting. It's the seed value. So what we're taking advantage of with these machine learning algorithms, this randomness, is a stochastic property. We want to take advantage of the randomness of a population. We want to sample from population P. We want to make these sub-populations and then build a relationship off of it. But the challenge you run into is if you were to then come back to it in an hour and run it again, you might get a different result, or someone else might get a different result. So you have to set the random state. And so that's where you set the seed. And we'll do that in the random forest script. But that allows you to set the same properties for your stochastic behaviors. So that way you get the same repeatable output using a random property. So someone much smarter than I circumnavigated that a long time ago. So just make sure that your random seed is set. So I've got this script up here, and let me make it a little bit smaller so everyone can see. We only have about 20 minutes. Go ahead, Frederick.
I think it's Jacob. Jacob?
Oh, Jacob, go ahead.
Hey, Tim. Yeah, I just raised my hand because there's actually another question in the chat. So I just wanted you to check that out.
In EO data, they are mostly spatiotemporal and during sampling and training. How do we manage to randomly select from a certain temporal period or spatial location? Okay, yes, that's a challenging question, and I would say it's mostly related to study design. So for instance, I'll go back to this rice mapping effort because that's just fresh on my mind from some of the work that we did in the HKH region. But rice is grown at a particular time. There's a transplanting stage where it goes out in the field, and then there's a flooding of the fields. So there's like this water presence, and then the fields are drained, and there's a harvesting, and then there's refertilization. So there's a cultivation practice that happens. It's very, concrete. It happens at the same time every year, maybe 1 or 2 days flexibility. So we can key into those phenomenon, that those changes on the landscape, with sub-selecting those temporal periods. We did a lot of testing as to, what's the particular time frame. Should we do every 15 days, every 30 days, every 6 months, a full year? When do we develop those composites? But we really dialed into the farmer behavior and the cultivation practices. And the same thing could be happening for any kind of phenomenon. You just need to sort of think about it as, what bookends are happening with this phenomenon, and how do I capture that with the right indices or the right, spectral information. And then for the spatial locations, I would say that's really tied to the variability on the landscape. If you're seeing a particular phenomenon happening in just one location, it's hyper specific, you may not need points from all around, the Sahel region, right? You might only need it for that location to model that behavior. But if you were to then project that, do that prediction far beyond the bounds of where you have that data, you're really sort of interpolating. You're just projecting what this model should be. But the confidence of that, those much further away locations, should be much lower. And random forest doesn't actually give you a metric to understand that interpolation. Other algorithms do. Maxent is one of the examples that actually gives you a value of when your model is starting to project into basically, it's giving you a good value, a good statistical value, but it's a low quality output. So different algorithms kind of handle this differently. I think that maybe answers your question. And I'll just keep zooming because we've got, we can't find the script. Okay, so when you open up the scripts on the left-hand side, it should be within Reader. So right over here in Reader, and it should be under TJM. So it should be way probably down in this location. And I'm just gonna, yeah, go ahead, Emil.
Yeah, I was just gonna say too, sometimes too, what happens is, even though it adds the script, you have to use the little refresh button at the top to kind of refresh, what scripts you have access to. So that same button that Tim is showing there. So after you do that, then it should show the TJM 0042 / West Africa ML training repository. So click the link that Tim sent. If it doesn't show up, just hit refresh and then it should be there. And if you still don't see it, then just let us know in the chat. Thank you, Kidia.
Yeah, that's a great point, Emil. Sometimes it has a weird lag. So I'll just keep moving along because this is more about, this is kind of the parting gifts. You can use this in the future as an example. And the scripts are relatively straightforward. So this first script is, let me zoom back up here, is associated with, under owner, sorry, SAR processing. So I won't go into this because this is all sort of remote sensing and not machine learning, but I wanted to just highlight that we have this very detailed pre-processing Sentinel-1 script to produce a radiometrically terrain corrected and Lee speckle filtered processed Sentinel-1 image for ascending. And the reason why we do this, what Emil brought up before, is understanding the quality of your input data, especially from the covariate side. You want to do a lot of pre-processing and understand the pre-processing to get a product that's valuable. So the GRD data that's available in Google Earth Engine is not great. So we added this script to basically produce this pre-processed image collection, and then it's available in the next script. So this is one thing you can use in the future. It's essentially just it's a pre-processing script, but I didn't want to just skip over that and let you guys have it and think about it. So we'll just jump down to the second script, which is the meat of what we're going to be talking about, and that the final image collection from script number 1 is available in here. It's just an open asset that anyone can use. So feel free to read through this. It's got 9 distinct steps in this code. All of it is already commented out. So we'll just go very quickly through this code and uncomment it together. And then we can ask questions. Feel free to stop me at any point. So let me, okay. So first step is we're going to define our date and our region of interest. So I've arbitrarily selected 2017, just looking at some of the Galamsey data that was available in the West Africa Google Earth Engine asset space. And that seemed like a good input for the Galamsey data and also the EO data. Thinking of SAR, it's not available really until 2017. So we wanted to select a later time step that had more covariates available. So then we've got Ghana, and we selected that country. And we've added a geometry. So we don't want to look at the entire country. We want to just look at a sub-region. So that is this geometry right here. So let me scroll in. We've looked at this smaller location near the ocean, and then we've just intersected that location with the full country. So if I hit run, with just these few lines included, we can see here that we've got this ROI, which is this location, right? It's that box intersected with the country bounds. So now we want to add in some input variables. So I'm just going to go to the section 2 and uncomment all of this. So we've got Landsat 8 surface reflection, and we've got Sentinel 2. And I just pulled in this Sentinel 2 example from some of the other Galamsey scripts that Jacob had shared with me as well, that are some of the other approaches that are being used. So I'm just kind of grabbing different data sets. By no means is this the way it should be done. Definitely take more time and sort of understanding the nuances of each of the input EO data sets. But I just want to get a lot of examples here so we can run the algorithm. So we've got Landsat 8, Sentinel 2. We've created these NDVI composites with Sentinel 2 in particular. This is taken from some of the ongoing work at West Africa. So if we add this, we hit run just in step 2, all it's doing is basically adding these to the map. So we've got some data, which is great. Let that load. Perfect. So we've got some input data. Now, one thing we should be thinking about is, let's just uncomment all of this. We've got a single function here. That function is called optical indices. It takes an image collection and a region of interest. We've got a region of interest already. We've got a couple of image collections defined up above. And what we're going to do is we're going to remove all the clouds. So this first function goes into each image collection like a deck of cards, pulls out a single image, goes across every pixel, identifies where a cloud might be, and removes that pixel. So that's the first thing. Then it takes that single pixel information and performs an operation on it. So it might do an NDVI, NDWI, all of these different indices that are being produced. So it does all these calculations and then puts that card back in and produces a new image collection that we return with a single image collection with all of these bands added. So it's a very strong, pretty mighty set of scripts here that produces all of these different indices automatically. So we've got this optical indices here. Here's a trick question. When we hit run here, what happens? This is kind of hard. Like I told everyone, it's a trick question, right? Nothing will happen. That's the trick. Because we're not calling this function on anything, right? In Google Earth Engine, it's not going to actually run until we have it applied. So this is just, we've defined a function. We haven't said run on anything just yet. Okay, and then we add in our Sentinel-1. This is that indice, the preprocessed indice that's available within the asset space. Everyone should have it as well. It's just the ascending Sentinel-1 preprocessed. So now we want to apply that function I mentioned before. So we've got this variable, which is optical indice out. It's taking in our Landsat and our region of interest, and it's producing all of our indices that we mentioned before. Now, in addition to all of that, once I hit run, we added a couple more data sets. We added a JRC data set, which is it's from Peckel et al. From JRC. It's total water occurrence over like a 50-year period using all of Landsat. Obviously, because Galamsey is highly tied to water changes in water, this could be a great variable. And then we've also taken in this urban population and looked at locations where there's urban centers, because obviously Galamsey is not happening in city centers, and those phenomenons between urban and Galamsey kind of are very close to each other, right? So we wanted to get a variable that helps to sort of distinguish them. So we've done this aspect right here. If I scroll over, we've got this variable called band prep, which adds the shuttle radar topography, our elevation, all of those indices, JRC, the urban population, as well as the Sentinel-1 and the Sentinel-2 final NDVI. So we've got a ton of bands we've just added all together. And essentially this has created a single table. This is a feature collection that has all that information for us. So when I hit run in the console, we can see here, this band has 20 images, or has 20 elements. So the normalized difference ratio for Sentinel-1, the settlements from the urban information, the maximum extent of water from JRC. So there's a lot of nuance here that we could go into further detail. I know we're running kind of out of time, but you can see here all these different bands, which have some logic as to why we would include them. Okay, so now let's get into the data prep aspects. So this is where you can get engaged. You can do this on your own. If you read through here, this is where you're going to add a marker for each of the locations. So if I scroll up here, we can see that I've added a user added Galamsey and a user added non-Galamsey. And if you click on this point, this is CDI 1. So that's all the locations that are Galamsey. And you can just scroll into the map and find all the locations. Let me zoom in where there is Galamsey, and you can add more points. And this is just, I wouldn't necessarily recommend it for a study design, right? You want to make sure you've got good field data. Maybe you're using Collectorth Online. But for the sake of running this algorithm, you can add more data this way. So you can just go ahead and add more locations if you want. And you could add for your non-Galamsey, we've got intact forest. I can just add some more non-Galamsey. And these points are already set up to have a 0 for all of these locations. So this is the non-Galamsey locations. So that makes sense, right? We're adding more and more training points that are spatially distributed. Again, you want to apply more restrictions on good rules of thumbs in the future, but this is more for just getting the algorithm to run. So this walks you through adding more locations. You can just do it at 20 or 30, what have you, for each of them. And I've already included some to begin with. And then let's go ahead and open up step 5.3. So if we hit run on step 5.3, we can see that, let me make this just a little bit bigger. Okay. When we run this, we've got this user added locations. It's telling me that I've got 28 user added points for Galamsey and 100 already to begin with. I just added a couple more. But then at the same time, we are also adding the 2017 points that are available, right? So then we want to add this data together. So this is where we take anytime the CID is considered 1, we want to convert that into being a Galamsey point. So we're just doing a little bit of data handling here to make sure that the input data is 0s and 1s for Galamsey and non-Galamsey. And we're selecting that year. So the final output here for this Galamsey points, if we look at it in the console, first example here, properties, CID 1, year 2017. So it does all the handling already. And that's what we want to give to the algorithm. So now let's go into step 6. As I race against time, we've got this training sample. So essentially what we're doing is we're extracting. We've got a location where across the entire study area, we've got all these pixels, and we want to go and select for these locations where we've got input information, and we want to sample that region. So we want to go to that geography, we want to go to that feature collection and sample the Galamsey points and that label information. So this is creating our training sample, right? Thinking back to the theoretical aspect, we did all this work to create good training points. And we add this random column where essentially we split the data 70-30. So we have 70% of the data used in the training and 30% used in the testing. It's pretty standard approach, but this is what we're using here. Okay. So this is when we print this, we can see the dynamics of the data. So this could be a good measure of when I talked about the balance of your data. Let this run, and we can see what for our testing and training, how many points we have. If this is running, I think it is. Okay. It's thinking. I'm skipping ahead while it's thinking. So it's calculating, as it's doing the sample region, it's calculating all of the features that are in there. Just minimize that while it's still thinking. So then the step 7 is where we define a random forest. So if you were to read the documentation on the random forest within Google Earth Engine, it needs a feature collection, a list, and an image. So we've created a function here that allows you to do all the operations that you need in a relatively straightforward function. Essentially what this does is it pulls in our feature collection, which is our training data, which we're sampling now, our list, which is our band name. So that's this right here. Or our list, excuse me, CID is our label. So that is we considered CID as being presence, 0 or 1, 1 being Galamsey. And that's within the feature, right? And then our list is up above. So then we've got all the information we need for the random forest right here. And so I'm just going to go ahead and add step 8 because we're running out of time. I apologize. And hit run. So we have a product to work with here. Let me make this a little bit bigger. Uh-oh. Here we go. Okay. So now we've added all the layers in the random forest. So when on step 8, this is where we're actually applying the random forest model. Training data are bands, which is these 20 bands right here. And then our band prep, which is that image, which is well up here. Band prep. Excuse me, right here. Yep. So this is that image of all of the different bands. So this is what we give to the algorithm, and it performs in this function here, and it provides all of these outputs. So it's going to provide a chart of the variable importance when it's by performing the random forest, it's going to use this .explain to take advantage of the decision tree that is being produced, and it's going to then plot this information in this histogram. So if we open this up, we can see here that of the variables that we included, settlements, MNDWI, NDWI, so these water indexes, settlements, and the normalized difference ratio of Sentinel-1 seem to be important while these other ones are not. Again, this is just a tool to be thinking about when you're in that iterative modeling stage. And then we've got all of these different metrics, which we can go into detail more if you want, but we're out of time essentially. And you can see the model being performed here. So let's zoom in. This isn't the world's best classification, but it could be useful, right? All models are wrong, some are useful. And we can see here, just with some indices and about 30 seconds of that run, we can see here that we've got a classification that's able to identify relatively well some of the Galamsey locations. It's also misclassifying pretty significantly as well. Like right over here is a great example. So this is exciting. Definitely check this out. And then I'll end with this final script over here on script number 3. It's a little bit more detailed. It's the entire script for the complete lab with far more training points. So you've got 400 non-Galamsey points. So the model output is much better. And you can just go ahead and try and run through that. So let me zoom back to the correct tab here. All right, so we've got 2 minutes left. It's hard to do a training virtually with an hour and a half. So this is a walkthrough of all the steps that we just did to produce this Galamsey classification. And you can use this model to really understand how did it perform. You can take advantage of the statistics that I very briefly mentioned to understand the accuracy of it. I think if I zoom back to the tab over here, as it's sort of sluggish, the accuracy was, for the training accuracy, was 99%. So we know it got wrong, right? We got locations incorrect. So just because it's giving you a good statistic doesn't mean the model is good. So just be thinking about that. What we're actually identifying, just add a caveat to some of these statistics when you're reporting them, because it might give you a really high value, but when you look at it on the map, it might not make perfect sense. So you might want to use a different statistic like Cohen's kappa coefficient to help sort of tease out the value of your final product. Okay, so we've got a minute left. I think we still have time if a couple people want to run a little bit long to do the Kahoot, the final test to see who the winner is. So let's put that up because I know we're already over time, but I feel like we'd be losing out on a good opportunity to do a fun test. So let me share this tab. Stop sharing and then share this tab. Okay, this is a little slow, but so I know we're over time, but if everyone wants to, you can participate. You just need to go to kahoot.it, and then you can add in this pin. This will allow you to join the game, and there's about 5 or 6 questions, and we'll dawn a winner, keep the excitement high for when we jump into deep learning, and hopefully we'll have a lot of discussion space also. I know I ran over on the discussion time, but see Sabiri, feel free to add in everybody else. And I'll give it like, a couple minutes. I know that's Emil. So while we're adding folks, let me read through the comments because I know I ran long. If there's anything else. Can't find the script, me too. If that didn't work, okay, here's the script. So yeah, as people are joining, any questions as I zoomed through the random forest? Well, one thing I'll mention as people are still joining in, if you look at script number 2, Google Earth Engine is taking a long time to load today. Within script number 2, there is, within the random forest step number 7, there is properties like numbers of trees, variables per split, minimum leaf population, bag fraction, number of nodes, and seed. We set it as 7. That's the stochastic behavior that I mentioned before. Those are all model parameters that are just set. So if you want, you can change those numbers. And the value of that is you add more trees, that's just more models that it's going, like laterally, right? But it just ends up being more computational effort. So just think about that as, one of the negatives of adding more trees, but the value is you get more variability, right? You control that variability. So you can play with those parameters on improving the model process. And that's sort of the iterative component there. But for when you actually do implement the random forest that we ran through, you can see how simple it was, right? It's just making a decision, drawing that hyperplane based off of those 20 variables that I gave it. So I see we've got 19 people in with 45 people in the call, excluding myself. I'll give it a few more minutes if people are still switching over. It's just the kahoot.it. Okay, we've got 20 people on. Let me mute this also because it makes funny music. There we go. Well, I don't want to leave anybody out. Who else do we got? A couple more people that should probably join in. Join the fun. Give it another minute. There we go. A couple more people joining. I like this. Someone's named Cool. It has a fun looking fox. All right, we're at 24 people. We're going to do it. We're going to roll. Okay, so for everyone who hasn't used Kahoot, the way this game works is we're going to start the quiz, and then you have to respond. And you get points for being accurate, right? If you know the answer and you correctly answer it, you get points. You also get points for how fast you answer. So at the very end, it's going to tabulate not only how fast and how correct you were. So you get more points for being correct, but you get additional points for being fast. So I know we're challenging network issues, but this is all just for fun anyways. So let's go. Okay, machine learning algorithms build a model based on blank in order to make predictions without being explicitly programmed to do so. So they build models on blank. Is it garbage in, garbage out, training data / sample data, cats and dogs, or inference / prediction? Nice. Okay. Got some good answers. All right, so you can see how fast it goes, right? Not only do you have to be able to get it right, you have to do it quick because there's only like a 30-second timer. All right, next question. Oh, we can see the scoreboard first. Narha is winning right now. Just barely, though. The Kahoot link. Okay, and then let's go to the next slide. Okay, true or false? An input feature is an individual measurable property or characteristic of a phenomenon. True or false? Getting a lot of responses here. Okay. 2 seconds, 1 second. Nice. A lot of good answers. Let's see what where the scores shake out. Mary zooming up the leaderboard. Very nice. Okay, next question. True or false? Decision boundary is a hypersurface that partitions the underlying vector space into two sets, one for each class. True or false? Nice. A lot of good answers. Okay, let's see where everyone shakes out. That's awesome. Okay, look at all these people zooming up the leaderboard. Highest streak, three answers in a row by Aziz. All right, next question. True or false? Random forest uses bagging to randomly select features in order to construct a collection of decision trees with uncontrolled variance. "21 answers. Ooh, split camp down the middle. All right. That means we got to go back to that one. Okay. Let's see where we're at. Ooh, zooming up. All right. I think we maybe have 2 more questions. True or false? Diversity of solutions is a valuable trait. True or false? Nice. Yep. That's great. Okay. Maybe this is the last one. Let's see. It's a close race. Everyone's in the same sort of space up here. All right. Random forest is a blank learning method for classification that operates by constructing a multitude of decision trees. Is a ubiquitous, a single, an empty, an ensemble. Random forest is a blank learning method. Nice. A lot of people put in ensemble. That's wonderful. Okay. Next. This might be the last one. See your scoreboard. Sabiri well out in front now. Okay. True or false? George E.P. Bach said all models are wrong and some are useful. True or false? Nice. Okay. Let's see who was on the podium. Mary in third. Sabiri in second. Jacob takes the lead. Nice. At the very last. Oh, that's awesome. Well, a round of applause to everybody for having a good time at the very end. I know we ran long by 10 minutes. This is day 1 of 2. So I know I just zoomed through the code, which is probably what everyone wanted, but we'll have time tomorrow with some discussion space as well. Yeah, and Foster, go ahead.
Yes. Thank you very much for the GEE script. And so I just wanted to find out if you think that from your experience, the random forest algorithm will do as good, given that it's simple to implement and not too expensive to use. So I just wanted to find out your take on that in relation to our wanting to adopt a deep learning approach. Do you think we can go for a machine learning or a deep learning approach? Over.
Yeah, great question. I feel like I'm constantly sort of thinking which one should it's like you're shopping for a car or a house, like which one should I buy? What do I really need? And with something like random forest, it's very simple to implement. It's relatively easy to understand where you came from at the very beginning to your final product. Obviously there's some space within the random forest that's sort of decoupled from what is easy to understand. That's the black box nature of it. And because say for Galamsey, the phenomenon that you're sort of looking at of impacted riverways is relatively easy to distinguish between forest and urban, right? That class isn't very well mixed. You can identify it pretty easy from space, which we just did in that random forest example. So in that sense, it's pretty straightforward. I think you could get away with a random forest model and just really fine tune it. To your other element of that question, though, of deep learning, I think it's really valuable to learn deep learning, like to actually have that skill set and leverage it, because the field as we know it is really advancing in that direction, because deep learning takes advantage of more and more data. The random forest, you're going to have to go and conduct these field samples every year. It's really data intensive in that way. As opposed to deep learning, it's even more data intensive, but it can rely on even more and more data that you may not even have to collect. So like the field as we know it is really sort of shifting in a way that you're going to be able to take advantage of more and more data sets and get a conclusion that's really valuable, all in theory. And the other element that's really valuable to deep learning is it's not tied to a single pixel. Like we did that example of dropping points in the code, and it's going to build the model in random forest per pixel classification. But you can actually use deep learning to do a full area, so like a neighborhood of pixels. So you're taking a patch of pixels and then taking the feature space within that neighborhood of pixels to develop a model. So it can actually look at like a wider phenomenon. So you're looking at a bigger aperture of space. And that's super important when you have a really complex challenge, really tangled data in that sense. So there's pros and cons on both sides. And Foster, to your point, I think if I would always start with doing the simplest approach first, like, can you identify galamsey in this example with just a spectral analysis, right? Looking at NDVI change, is that enough? And if that's the case, that's so simple. You can course correct and you can develop a service that really leverages something so simple like that. If you can't, then maybe try a regression or a random forest. And if that still doesn't net value, then you can go to like deep learning and really sort of start tackling that tangled data problem with an even more complex set of tools. So that's what I would recommend, just because those other simpler solutions are still super valuable. Any other? Oh, go ahead, Glory.
No, I'm fine. Thanks. I thought other person put up his hand before. Okay. Maybe we should start rounding up now.
Yeah, I think if there's no other questions, if you do have questions, write them down, and we'll have some space at the beginning of the day tomorrow to address them. Take a little bit of time looking at those scripts that I shared, because I know I just zoomed through them, but we'll have some space to talk a little bit. And this is all about getting everyone sort of excited about machine learning and deep learning, to ask a lot of questions and participate in the TensorFlow working group. So definitely be prepared for tomorrow. And thank you all. Bako, I see your hand up. Over to you.
Yes, thank you, Tim. So I have one question or concern. So for those who are beginners or almost beginners, do you think that it's not so? Is it easy for them to follow? Thank you.
Yeah, it's a good question. It's hard. I would say it's super challenging to see how well a training like this lands, just because it's virtual, right? You know, you're not really able to walk around a classroom and see how people are progressing. So that's where I really rely on everyone to let us know on the training side what doesn't make sense, and you add in the factor it's a short amount of time. So those are the things we're up against. So definitely let us know what could be valuable, and we'll also have the beauty of this, Bako, is that this is the very beginning, right? So if folks are really still interested, like this is just scratching that initial itch, we have a global group that meets every 2 weeks that starts asking these questions and gets folks sort of more skilled in that direction. So we've got a couple mechanisms in place to make it valuable. And I think I maybe put the onus I'm wearing my teacher hat here, to the students. You know, it's for everyone who's participating to find the value of the training, right? And then come back to application questions. How do I use this? I don't understand these 4 components, but I want to understand these 4 components. How do I get to that end product? And I think we've got great success in the past with working with a lot of the different hubs to sort of get to that sort of operational space. So hopefully that answers your question and spurs folks as well. I see a couple other questions on switch over.
Add on what Tim is saying. I think it also comes down to how hands-on you get with your own problem. Again, this is just a pointer for you to get started, and there are like plenty of materials out in the internet that you can always go back and refer to. But again, it comes down to the problem that you're trying to tackle, and how heavily you want to get your hands dirty. And it's always going to be like learning by doing. So yeah, just to add that out there.
Yes, and then to also add to it, Tim, the idea first of all for this training was so that we use it as a launch pad in West Africa to actually start a regular meeting that will help all of us ask questions and try to solve problems together in West Africa. Now, in the process of that, if we have any need to actually call you or somebody else to come and talk to us, we will do that. So I want to encourage every one of us that is in this meeting now to be ready to join a group, which I will send out a call. And if you are interested, please join us so that we take this step by step. I mean, like Barco said, some of us are in the very low end of things. We can grow ourselves together. And then we can bring in Tim and Biplov and Emil and Jacob as we go. So I will send out that call and we shall start that. Yes, Tibi.
I just wanted to say that I think it's really interesting. The Glory, we need to think of mainstreaming this kind of training in a hackathon mode where we can work some kind of online hackathons, because I think the kind of audience that we have and some of the newcomers that we have on the team would be very comfortable running these kinds of distributed online hackathons for particular tasks. And I know that we've discussed it in some cases in the context of Galamsey and new activities we could have to add to what Foster's team is already doing. But I think that this needs to be mainstreamed, and it goes really well with the kind of new approach we discussed, Glory, on the capacity building. So I think that's matter for thought in the course of next year. I think as we prepare for the annual work planning meeting next week, those are the kinds of activities that I would like to see, because I think they will work very well. Over. And thanks to Tim.
So thank you very much, Tim. I think we should start rounding off. Thank you very much, Tim and Beplo. I want to also thank everyone that has joined. Please, it is important that you fill the what do you call it, pre-test form. By tomorrow, I'm going to also send a post-test form. Please, it's very, very important that you fill it. If you need me to send it again to you, I can do that. And then also, it's also important that you also fill the attendance sheet. I'm going to send the attendance sheet to us after now. So we meet again tomorrow at same time, 3 p.m. in Nigeria, 2 p.m. in Ghana. I think it's 12. What time is it in? 9 a.m. in the US, and so on. Thank you very much. Yes, Tim, over to you.
I just want to say thank you all for attending, asking good questions, feeling the ability to stretch, go into new territories. It's always a fun experience. We're going to have the great opportunity to listen to Biplov tomorrow, talk about deep learning. Super exciting. It should get your gears turning on like, wow, I can't believe this stuff is possible. So thank you all. Write down your questions because we'll hopefully have some space. I know I just zoomed past it all. Thank you to Glory for setting all this up and being such a great team player. It's fantastic to work with him. And I'll see you all tomorrow. Thank you, everybody.
All right, team. Bye-bye. Thank you, everybody. See you tomorrow.
Okay, thank you very much.
Please don't forget to fill the form. Thank you.